Okay, guys, in this video lesson, we're going to get into friction and talk a lot more about what is friction and how does friction kind of work, okay? Because friction is a big part of our world. It just is. Now, within friction, there are two types of friction, okay? That is kind of key for us to realize is that we have friction that starts off as static friction, okay? So static friction is friction that happens when something is not moving, okay? Something is at rest, okay? So imagine you have a dresser in your room and you're trying to push it across the room. So you apply a force to that dresser and it does not move from that carpet. You're basically applying against static friction at that point, okay? Or you have a car sitting at a stoplight. Okay, to get it to move, there is static friction that you need to overcome to let it move because friction always opposes the motion. Okay, now we symbolize that F sub S, so it's friction for static, and it's at rest. It is about the start of the movement. Okay, now static friction, as you push on something, it is always going to be relative to how much force you put in it. So if I put 10 newtons of force into an object, okay, so let's go to the board here. Let's say I have, a big dresser I'm trying to push. Okay? And if I apply, my force applied, let's say is 10 newtons. So if I apply 10 newtons of force and the dresser does not move, that means that the static friction pushing back on me is a negative 10 newtons. That would be my friction static, okay? Now, if I apply 20 newtons and it still doesn't move, now it goes to 20. If I apply, let's say, 40 newtons and it still doesn't move, now it's 40 newtons of static friction, okay? So static friction can grow with how much force you are applying. Now, at some point, if I apply enough force here on my dresser, let's say at 53 newtons of applied force, the dresser starts to move. Okay, at that instant, it moves. Okay, that means that essentially that 53 newtons of force is the friction static's maximum amount. Okay, so the point right at, or basically the instant before it starts to move, is a maximum amount of static friction something can have. Okay, this number is important to us because that tells us the break point between moving and not moving. Okay, is our static friction maximum value. Okay, now once you get it moving, okay, once you have it moving, we no longer have static friction. We now have kinetic friction. Okay, kinetic friction, we saw F sub K, is always in motion. Okay, it's the friction it takes to keep things moving. Okay. The nice thing about it, as long as you maintain the same surface, you maintain the same, wheels and slides and angles and everything, as long as you don't change a variable, kinetic friction is always constant, okay? Which means it'll also always be less than the friction that's static the maximum amount, okay? So here's what happens. If I'm trying to push this dresser and I first make an applied force, it's going to apply, I'm going to keep moving up, I'm going to keep applying this force. At some point, I'm going to get to my friction static max, and then it's actually going to drop down, and then from here on out, I'm going to have kinetic friction force against it. So we actually hit a peak, and then it flatlines off of that, okay? Now, when you take a look, here's a graph of that idea, okay? So we have our static friction coming up. At this point right here, we've hit our maximum static friction, so you might want to label this F sub S max right here. Okay, this is our static friction side, make sure you label that. Here's our kinetic friction side, make sure you label that. Once it's moving, now it stays the same. So this is not moving over here, this is moving over here. Okay, so again, if you're taking notes with this, you might want to write down not moving, moving over here. Okay, think about it. This happens to us all the time. If you're trying to push or pull or move something, it usually takes a little bit more energy to get it started. And then once you get it going, it's easier to push, okay? I used to watch those tough man contests when I was like in college, that kind of stuff. They entertained me for some reason. And it was always interesting, the announcers on the thing, they'd be talking about how strong and big these guys were, and they're pulling like buses and airplanes around and that kind of stuff. But every single time that guy would start and he would just lurch into that harness that they put them on, and the plane would move a little bit, and the bus would move a little bit, and they would start walking, and they get this thing moving behind them, this plane or bus is moving behind them. And as long as they kept moving, they could get to the finish line. However, if at any point in the route it stopped, they lost some traction, they lost a little energy, whatever it was, they almost never were able to get it moving again, okay? And it's because they had to re-go over this idea of static friction. So it took them all this energy to get it moving, and then once they got it moving, they could actually apply a lesser force to keep it moving. Okay, so this idea of kinetic friction is actually once we get things moving, it's actually less amount of friction. Okay, that's why also start and stop traffic is harder on cars because you're overcoming static friction to start and stop your car all the time versus just driving down the interstate. Okay. Okay, now we can actually calculate friction force. Okay, so how much energy does it take to move things back and forth, and actually put some numbers to this thing. Now, friction is dependent on two different variables. Okay, we have the weight of our object. And we also have the surface in contact with each other. Now, if I just draw a block on the board, and I know I have the normal force pushing up on something, and I have the force of gravity pushing down on it, okay? But I also have the surfaces at which are in contact with each other, okay? So friction is dependent on these two surfaces that are in contact, and it's dependent on the weight of our object. Okay, so two different things. Now keep in mind, we know that force of gravity is equal to the mass times acceleration due to gravity. Okay, and we're going to use this because usually we want to know we usually know the mass of the object, so we usually know this in kilograms. We don't usually necessarily know it in newtons. So if we know the mass of the object, we know the acceleration due to gravity, we can always figure out what that force of gravity is pulling down on us, okay? Now, each of these things have what we call as a coefficient of friction, okay? A coefficient of friction is basically a ratio between the friction force generated to the weight applied. So how much friction is being generated here versus the weight being pushed down on it? That's our ratio between those two things, okay? We symbolize it with the Greek letter mu. Okay, looks like a U with a little kickstand out front to it. And because it's a ratio value, there are no labels to this thing. Okay, so let's take a look at the actual equation that we generate to make its coefficient of friction. Okay, now notice it's a force divided by a force. So newtons divided by newtons would be no label. So we can say that for static friction, the coefficient of friction, so this right here is our coefficient of friction, mu sub s for static, is going to be the static friction maximum value, so that peak of our graph from before, divided by the force of gravity. Over here, same idea, I just substituted in the force of gravity for mass times g because often we need mass times g. Identical equation for kinetic friction. So we have mu sub k, now it's the force of friction kinetic here over gravity, again just substituted in again, all right? So if we wanted to know, how much the coefficient of friction was for this object, we could actually solve for that. Okay, we actually could figure out what is that coefficient of friction. Okay, now coefficient of friction, basically what they do is they kind of tell us how slippery something is. All right, we put two things in contact with each other, and they slide past each other. If they have nice smooth surfaces, or if there's some sort of thing that keeps it nice and slippery, we can. It would be a lower coefficient of friction. If it was something that is really rough or had a tendency to stick, that would have a high coefficient of friction. Okay. Now, what it does to us, it compares the Fx or Fk with a force to lift our value. So the lower it is, the less friction we have. We have three possibilities here. Okay. First one, coefficient of friction is greater than 1. Okay. That means it takes more force to slide than to lift. Okay. This would be something like rubber to concrete, okay? It's going to take us more force to slide rubber, a really sticky surface, across a really rough concrete surface than it would be just to lift it and carry it to the next spot, okay? You can have mu equal to 1. That means the forces are equal to each other. So the force it takes to lift something up would be the same as sliding it. And then, of course, we have mu equaling less than 1. So it takes less force to slide than it is to lift, okay? We would say that's kind of a slippery surface. Now, typically, if you're trying to figure out how you want to move an object, if you have coefficients of friction less than 1, it's easier just to slide them along the ground. Okay, think like a sled on snow. If you have coefficients greater than 1, Okay, it's really hard to slide them, so it might be just as easy just to pick them up and carry them to one spot and set them down into a different spot. Okay, we have different coefficients of friction here for us. So rubber on concrete is about 1. Okay, so it's about 1 in terms of what we have. That's for static friction. Coefficients of kinetic is 0.8, a little bit less. Okay, steel on steel, aluminum on steel, glass on glass, copper on steel, wood on wood, and so forth and so on. This one is variable because different types of wood have different grains to them, that kind of stuff. Of all these numbers, the one I think is kind of the most important or kind of the most interesting one is way down here, synovial joints in humans. Okay, so the joints in our elbows and our knees and our wrists. So what kind of friction do we have inside our bodies? We know that over time, our bodies wear out, right? We have, as you get older, you hear people getting hip replacements, or you hear that your knees go bad or your shoulder goes bad. That's because you build up friction inside there, you lose cartilage, that kind of stuff. But if you take a look, our friction inside our bodies, 0.01 is our static friction, and 0.003 is our kinetic friction. So we actually have extremely low friction inside our bodies in terms of our joint movements, which is, even less than ice on ice. So think about how easy it is to take a block of ice and slide it across another block of ice. Okay, just to get it moving for us, it's even easier inside our body. So we extremely low friction. Okay, in terms of what we have. Now, wax wood. This one is not, we don't know for sure what that is. Probably because I would guess with dry snow, it probably depends on the snow. And dry snow is really powdery, so it kind of depends on how you compact it. I would guess this number is really hard to calculate. That's why that one's a blank. Now, other thing we think about is we use lubricants inside of a lot of things. Inside your engine we have oil. We always spray like Pam or something on our pans before we cook food inside it. And what we're trying to do is we're trying to create some sort of barrier between our two surfaces that allows basically movement. Any surface we have, even though we think it's perfectly smooth, even like perfectly smooth glass, actually has microscopic rough edges on it. And those microscopic rough edges actually can catch on each other and they cause friction. So what a liquid does, or what things like oils or like Teflon, spray coatings and that kind of stuff, what they do is they provide this really tiny little liquid layer that creates a different surface to surface. Okay, so instead of having aluminum on steel, we have aluminum to oil and steel to oil, and that basically fills in all those little gaps and creates a much lower friction surface for us. Okay, so that's why we use lubricants, is because they actually generate a lower coefficient of friction. Lower friction means less heat buildup. Less heat buildup means that the things that we work with last longer. Okay. Now, what we want to do is let's actually do a little problem here and solve for this. Okay. So let's say over here I have, let's say my mass is 15 kilograms. Okay. And let's say I am doing two surfaces. So let's go back to our chart. And let's say I have a steel on steel. So this is a steel block. This is a steel surface. So my coefficient of friction static for steel on steel is 0.74. Okay, is 0.74. So how much force would I have to push in this direction to get the block to move? Okay, that's what we're going to solve for. We know the mass, we know the coefficient of friction. How much force do I need to get this block to move? Okay, so if we go back to our equation, we know that the coefficient of friction static is equal to the friction static max times the mass over g. Okay, so we know our mass, we know g. We're going to solve for the static friction maximum. That tells us how much static friction is pushing this direction, so my force applied will equal that amount to get it to move. Okay. Static friction, or sorry, mu sub s is 0.74. Mass was 15 kilograms. Acceleration due to gravity is 9.81. meters per second squared. So now we can solve it, okay? So what I'm gonna do is take my 0.74 times this, and that will equal my static friction maximum. So 0.74 times 15 times a negative 9.81. And I get a value of a negative 108.891 newtons. Okay? It's negative because that's friction, which always opposes motion. Okay? It's always opposite of our motion. Okay? Meaning that we have an opposing force here. So the applied force would just be the positive version of this. So the force applied would be 108.9, but we'll just call it 108.9 newtons of force here. Okay. I only had two significant figures, so technically we should probably call that 110 newtons of force applied for this. Okay. That's friction. All right. In our next section, we'll talk about what happens when we don't push and pull at straight angles and we make it two-dimensional. Okay, guys, that's it. Thank you.